This lesson shows how the balance viewer can help you adjust hot runner system balance using in-cavity sensors. It also gives you some examples of how to solve problems with it. We'll cover balancing a tool at startup with cavity pressure, then do the same with temperature sensors, and then detect an out-of-balance condition. Note that the cycle speeds for these frames are not to scale but adjusted for the pace of the presentation. Let's begin with balancing at startup. Here on the first shot you see a fairly dramatic imbalance. There is even a pattern with the center and outer cavities tending to be opposite of each other. Then the tool warms up over the next few shots until it reaches a sort of 91% fill time balance. The autoscale mechanism on the balance viewer is set to keep about a 2% imbalance just visible from a distance. Now balancing begins by adjusting, in this case, tip controller temperature settings. Numbers 7 and 10 seem a little fast, so we lower the tip temperature settings for those two. Raising and lowering the other tip temperatures eventually brings the process to a 97% fill time balance. The time to fill the cavity is just one plastic variable, flow. We can look at balance in other ways. For example, selecting volume at fill shows the balance of cavity fullness at the point the machine slows down to pack. Selecting peak or cycle integral shows the balance of packing instead of filling. These values usually relate to part dimensions or the probability of shorts and flash. Note the dramatic difference in cycle integral even though the flow is balanced. The cycle graph shows a fairly tight group of pressure curves over the time visible on the graph. But if we expand the cycle graph, you see that the cycle integral varies because of differences in mold deflection and the way the mold springs back onto the finished part. This cavity shape variable may also imply a difference in dimensions. The cooling rate balance shows differences in shrinkage. This is affected by the cavity temperature, but it only makes sense when the front portion of the cycle is the same for all cavities. Cavities that are not well packed may shrink quicker than others. The balance viewer, when running, creates new balance numbers not generated by the standard eDart. Here are the three we just observed when we selected the buttons on the viewer. Here is an example of balancing a mold which has only temperature sensors in it. The eDart calculates the time from the start of flow until a temperature rise, in this case, process time temperature at end of cavity. You can see at the beginning of the run that the flow front arrival time is wildly imbalanced. With this much imbalance, some of the bars hit the top and bottom of the graph. You can turn off the autoscale and then adjust the values so that you can see them all. By adjusting controller tip temperatures, we eventually brought it close to fill balance. As we get closer to a good balance, we can turn the autoscale on again. Of course, this makes it look worse because the scales for that middle 2% are at a fixed size on the screen. So 86% balance looks poor, and it probably is. While waiting for the finishing touches, let's look at the other useful plastics variable that you get from temperature sensors, cooling temperature. The minimum is the temperature of the steel just before the plastic arrives. Clicking the minimum button, you see reasonably good balance between the cavity temperatures and thus the cooling. There is a pattern, though, showing that some are slightly colder than others. Here is an example of a mold running with reasonable balance in a rogue cavity. As a quick diagnostic tool, you can use the balance viewer to identify which cavity is the offender and decide whether it needs maintenance or adjustment. Notice that the other values show quite a different pattern of balance that is not related to the fill time. The cooling rate balance is terribly messy. This may be due to real cooling differences or to differences in the filling and packing of the cavities. Here we start with a fairly well-balanced fill. Since the balance numbers are just summary values like any other in the system, you can set an alarm on them. Here we'll set an alarm on the balance for cavity fill. Using this unstable replay data, I have to enter a value instead of waiting for it to stabilize. While trying to adjust the last pair of cavities into balance, someone, I confess it was me, adjusted the temperature too far and in the wrong direction. This shows how tricky it is to use the curves and cycle values for balancing. If I had walked away and not looked back, the tool could have run production out of balance. When it gets too far out of balance, our alarm that we just set goes off. This would show up on the Advanced System Overview or on a light tree to get someone's attention. Returning to the machine, I see that it is location 6 that is at fault and needs to be readjusted. Being low and slow, I raise the tip temperature to where it is supposed to be, and it returns to proper balance. If you have part sorting automation in place, you could discard those parts until the balance problem is fixed. This concludes the introduction to the Balance Viewer tool. Functions such as showing or hiding buttons, showing template values, balance lines, average, and so on may be available in future releases through the Setup button.
In keeping with the mood of the show, let us go where sheep may safely graze, shall we?